Hello everyone, welcome to my class. Today we are covering triple integrals in cylindrical coordinates. Let's start the class right away. We know there are three ways to locate a point in the space: by using Cartesian coordinates, the order triple xyz, by using cylindrical coordinates, order triple r theta z, and by using spherical coordinates, by order triple rho phi theta. And we know in Cartesian coordinates our triple integral template is we denoted by I in our last class. So I equals to triple integrals of function of three variables f of x, y, z over E, and we integrate it with respect to a volume element dV, and E is a bounded three-dimensional region. So now in these sections we wanna rewrite our triple integrals using cylindrical coordinates. That means we want to find the representation of x in cylindrical coordinates, representation of y in cylindrical coordinates, representation of z in cylindrical coordinates, and at the same time we will find a volume element in cylindrical coordinates. So let me start with the cylindrical coordinate system. Just to give you a first introductions. As I mentioned in B, our cylindrical coordinate system is represented by order triple r theta z. So let me explain this cylindrical coordinates using the middle diagram. So the point on the space is P r theta z, where r theta is the polar coordinates of the projection of P on the xy plane. So this Q is same as the polar coordinates, which is in the first diagram, and z is the same z as from Cartesian coordinates. So that means z gives the distance of point P from the xy plane. So in another word, cylindrical coordinates combine the polar coordinates with the z coordinates from Cartesian coordinate. And in the third diagrams, the point P generates a cylinder. So the name is cylindrical coordinate system. Awesome. So let me scroll down. There is an convergence formula from cylindrical coordinates going to Cartesian coordinates, and from Cartesian coordinates going to cylindrical coordinates. We put x equals to r cosine theta, y equals to r sine theta, and z equals to z. So z in cylindrical coordinates and Cartesian coordinates does not change, the same z. And as in polar coordinates, we found x squared plus y squared equals to r squared, and tan theta equals to y over x. And now the volume element in Cartesian coordinates, dv equals to dz dy dx, and now in cylindrical coordinates, this dx dy from here gives us r dr d theta, r dr d theta, and dz is dz. So the volume element in cylindrical coordinates is r times dz times dr times d theta. Great. So let's move on. So at this time, let's ask the questions to ourselves. How do we determine the limits of triple integrals in cylindrical coordinates? So let me recall the triple integral template here, where we represent a triple integral by I. So I equals to our integrand functions is f of r cosine theta. Now we replace our x, y, z by cylindrical coordinates. So our integrand function is f of r cosine theta, r sine theta, z, and then the volume element is r dz dr d theta. And in this order of integrations, dz dr d theta, our inner integral is z integrals, and our middle integral is r integrals, and our outer integral is theta integrals. So now at this time, I'm going to find out the limit of theta, r, and z. So in a special case, theta is in between two fixed values, r is in between two fixed values, but the surface z, the variable z is in between two surfaces. It's in the top surface and then the bottom surface, same as in the Cartesian coordinates triple integral. Then we can easily replace this theta by alpha to beta, r by a to b, and z by h1xy to h2xy. But in general, the polar regions from where we found the r and theta limits can be arbitrary. Let's say this is a radially simple. Radially simple means our radius are bounded by two functions of theta, and theta is between two fixed value alpha and beta. Then our domain descriptions, the polar region description is r between two functions of theta, and theta is between two fixed value. Then with these limits, our triple integral in cylindrical coordinates is I equals to triple integrals of functions f of r cosine theta, r sine theta, z, and the volume element is r dz dr d theta, where z is inner variable, r is middle variable, theta is outer variable. That means their corresponding integrals. So z integral is inner integral, r integral is middle integrals, and theta integral is outer integrals. So z limits is going from h1xy to h2xy, but now here is our outer integrals. For z, outer integral is theta integrals, and r integrals are the outer variable. So then we can write our limits for z. It can be the function of r variables and theta variables. So z equals to h1 r theta to h2 r theta. Same as in our Cartesian coordinates. At the times on our dz, dy, dx order in Cartesian coordinate, the z integrals depend on the two variables x and y. The same idea here. So the limits of z, or the bounds of z, depends on r and theta, and then for the r integrals, the limits of r integrals depends on theta, the outer variables, and for the theta, the limit must have a constant bounds. Hopefully this makes sense to you. Great. So now we do have a triple integral template in cylindrical coordinates. So let's apply this idea and solve the following examples. So let's start with example 0. It's the short and sweet example. Example 0 says, maybe let me scroll more down. Find the volume of a cylinder of radius a with height 8. So simply use the formula. The volume formula in triple integral is v equals to triple integrals of 1 dv. So dv equals to r dz dr d theta, and inner integral is z integrals, whose height is from xy plane to height 8, so 0 to 8. Then middle integral is r integrals, radius is a, so r equals 0 to a bounds, and theta in the circle, theta goes from 0 to 2 pi. Great. So now let's integrate. We can integrate separately. From theta integrals we got 2 pi, and from from the z integrals we got 8, and from the r integrals we have a r here, so r is square over 2. Put r value 0 to a. Put r equals to a, cancel this 2, then our final answer is pi a square 8. So we found the volume of a cylinder with height 8 using triple integrals in cylindrical coordinates, which we already knew. Pi radius is square 8. Awesome. Let's move on. Let's do example 1. Let me scroll here. Excuse me. Now example 1. Using cylindrical coordinate, evaluate the triple integrals of radical x square plus y square over e times dv, where e is the region that lies inside cylinder x square plus y square equals 16 and between plane z equals -5 and z equals to 4. So great. So first let's find the limits of our triple integral in cylindrical coordinates. So in cylindrical coordinates we are replacing dv by r, dz, dr, d theta. And in this order, first find the z limits. Z limit is going from -5 to +4. We found here. Maybe let's visualize first the surface here. The surface is, this is the cylinder, x square plus y square equals to 16, and the bounding planes are z equals to -5, which is in the bottom here, and z equals to 4 is on the top here. So obviously our z bounds are, lower bound is -5, upper bound is 4. So that's the z bounds. And for the r and theta, our projection of this surface on xy plane is simply the circle of radius 4, which is x square plus y square equals to 16. So the radius is 4. So then in polar coordinates, r varies from 0 to 4, theta varies from 0 to 2 pi. So these limits are coming from, this r and theta's limits coming from this circle. Great. So then in the solutions, given triple integrals I can be written as theta integrals, outer integrals, middle integrals, r integral, and inner integral, z integrals. And we know in cylindrical coordinates, x square plus y square is r square. So under the radical, that means simply r. So this r is our integrand function, and dv is the volume element r, dz, dr, d theta. Awesome. Then let's integrate. So from theta integrals, this is 2 pi coming from theta integrals, and for the r integrals, r times r is r square. So the integral with respect to dr is r cubed over 3, and these are the r limits, r equals 0 to 4. And from dz, from the z integrals, dz becomes a z, and put lower limit -5, upper limit 4. And in the next step, 2 pi, write down as it is, put r equals to 4, so 4 cubed is 64 over 3, lower limit is 0. And in the z, put z equals to upper limit 4, and then minus z equals to lower limit -5. So then 2 minus is plus, so that means 4 minus -5 is 4 plus 5, 9, which is there. Then simplify, this gives us 384 pi. So we found the value of this given triple integrals using cylindrical coordinates. Great. Now let's move on. Example 2. Use cylindrical coordinates to evaluate the triple integrals. The triple integral is given as I equals to triple integrals of x plus y plus z over e times dv, where e is the solid in first octant that lies under the paraboloid z equals to 4 minus x square minus y square. Awesome. So in this case, the surface, this is the paraboloid opening downward, and this is bounded on first octant. So first octant is this piece, this is. So then obviously for the z limits in the first octant, so z is 0 and bigger than 0, that means z is greater than or equals to 0 is the lower boundary, and the upper boundary is just the paraboloid, which is z equals to 4 minus, in cylindrical coordinates, x square plus y square is r square, so z bounds are here z lies between 0 and 4 minus r square. And for r theta limits, project this region in 2 dimensions, which is simply a quarter circle in first quadrant. Then the circle's radius is 2, so r varies from 0 to 2, and in the first quadrant theta varies from 0 to pi over 2. Great. So now let me go to the limits in the first column here. So the limits are z between 0 and 4 minus r square, r limits 0 to 2, theta limits 0 to pi over 2. Great. Now we can rewrite given triple integrals with those limits. So then I equals to theta integrals limits 0 to pi over 2, r integrals limits are 0 to 2, and then z integrals limits are 0 to 4 minus r square. Then in cylindrical coordinates, x is r cosine theta plus y r sine theta plus z itself, and then the volume element dv is r dz dr d theta. Let me scroll down. That's better. And then let's start integrating. So first write down theta integrals, write down r integrals, and also write down z integrals and multiply this r inside this parenthesis. So r square cosine theta plus r square sine theta plus rz, which is in this bracket, times dz dr d theta. And then first let's integrate with respect to z. So keep in mind r square cosine theta plus r square sine theta is constant for z integrals. So write down theta integrals, write down r integrals, then r square times cosine theta plus sine theta is constant, so its integral with respect to z is simply constant times z, then plus integral of rz becomes rz square over 2, and put z limits, z equals 0 to 4 minus r square times dr d theta. And in this line, so write down theta integral, write down r integrals, and then simplify these expressions using z equals to upper limit 4 minus r square and lower limit z equals to 0. When you put z equals to 0, lower limit, everything disappears, so put z equals to only upper limit and simplify, which is this expression here. And then the next, let's integrate in the next step, let's integrate with respect to r. So again, with respect to r integrals, these theta terms are constant. So 0 to pi over 2, this is the theta integrals, and then let's integrate with respect to r. So 4r square becomes 4r cubed over 3 minus r4 becomes r5 over 5. This is the constant, cosine theta plus sine theta constant as it is. And then for the integration of r over 2 times 4 minus r square is square with respect to r, it's a good candidate for u substitution. So let's do this integration separately. So put u equals to 4 minus r square, then its derivatives du is negative 2r dr. Then this r integral reduces to the u integral, which is 4 minus r square is u square times r dr. R dr is negative du over 2. And then the integration of u square becomes u cubed over 3. 3 times 2 is 6, and this minus as it is. And now to resubstitute back, this u equals to 4 minus r square, and that minus times this plus is this minus, and still I need to divide by 6, so it's 2 times 6, sorry, divide by 2, so 2 times 6 is 12, so this 12, u cubed, u is 4 minus r square, so 4 minus r square cubed, and then the r limits are r equals 0 to 2 d theta. Great. So this is the constant, this constant here, not there. So now let's put r equals to upper limit and lower limit and simplify, which gives us this last integrals with respect to theta. So theta integral is 0 to pi over 2, 64 over 15 times cosine theta plus sine theta plus 16 over 3 times d theta. Then this integral, the last integral, let's integrate with respect to theta. So 64 over 15 constant pull out, cosine theta becomes sine theta, and sine theta becomes a negative cosine theta, plus 16 over 3 times theta, theta equals 0 to pi over 2, and put theta equals to pi over 2 and upper limit and subtract, putting theta equals to 0, so this gives us your final answer 128 plus 40 pi over 15. Great. Let's move on. Let's do the example 3. Oh, this is better. Yep. So in example 3, it says evaluate the triple integrals by changing to cylindrical coordinates. So given integral is in Cartesian coordinates. Now we need to change this Cartesian coordinate to the cylindrical coordinates. So the given integral is I equals to outer integrals whose bounds are -3 to 3. The outer integral is x integrals. And then the middle integral is y integrals whose bounds are 0 to radical 9 minus x square. And inner integral is z integrals, z whose bounds are 0 to 9 minus x square minus y square, and integrand function is x square plus y square. So let's find out the corresponding limits for r, theta, z in cylindrical coordinates. Oh, that's better. So first, from this inner integrals, the z bounds are 0 to 9 minus x square minus y square, and we know x square plus y square becomes r square, so the upper limit for z is 9 minus r square. Great, we found the limit for z. Then let's go to the middle integral and then the outer integrals. So let's see what is the plane region they determines. So from the y integrals or y bounds, y is in between 0 to radical 9 minus x square, and then square both sides, y square equals to 9 minus x square. Wow, that's a circle of radius 3. And let's go to the outer integrals. Outer integrals limits are x equals to -3 to 3. So that gives me only the semicircle, the upper semicircles, which is this region here, which is same as here, right? Then let's write the limits in polar form. So in the polar form, we take a slice from origin or pole to this outer side. So r is 0 to 3, r limits, and for theta limits it goes from 0 to all the way to pi. Awesome. So now we have z limits, we have r limits, we have theta limits. Now we are ready to convert this integral in cylindrical coordinates and simplify. Great. So given triple integrals I equals to, this is the theta integrals, this is the r integrals, this is the z integrals. Z bounds are 0 to 9 minus r square, r bounds are 0 to 3, theta bounds are 0 to pi, and our integrand function is x square plus y square in Cartesian coordinates, which becomes r square in cylindrical coordinates, and our volume element dz dy dx in Cartesian coordinates becomes r dz dr d theta. Great. So now let's evaluate. So we can evaluate separately and the theta integral. So from theta integrals it gives us pi, and from the r integrals, write down the r integrals because one r is coming from this and z limit, and then integrate first with respect to z. So r cubed is constant for z integrals, so r cubed times z, and put z equals to upper limit 9 minus r square. So r cubed times 9 minus r squared dr. Now we have only one integrals, which is r integrals. So pi, write down as it is, and first FOIL r cubed send inside and take the integrals. So 9r cubed, integration of 9r cubed with respect to dr becomes 9r to the power 4 over 4. Then this minus as it is. R cubed times r square is r to the power 5. So the integral of r to the power 5 with respect to dr is r to the power 6 over 6. And then put r limit 0 to 3. Then put r equals to upper limit, which is this value, inside the bracket, and subtract the lower values, but for the values at lower limit, all zeros. So only put r equals to upper limit. This gives you this value, and simplify, which is 729 pi over 12. So we found the value of these triple integrals given in Cartesian coordinate by converting to cylindrical coordinates. The final answer is 729 pi over 12. Great. So we finished these sections. In our next sections, we'll study triple integrals in spherical coordinates. Thank you.